We are encouraging you. Dr. Belmar and I both have to be away most of the week of October 2nd, so we're giving you that. I think Brian already sent something around that we're giving you the week of October 2nd off. Well, giving it to you off from coming to class at 9 o'clock. If I were you, I would watch some of these other videos, okay, whether it's at 9 o'clock in the morning or some other time, because I think Brian sent something around, and somewhere around the end of the second week of October is when we want the one-page summary on one of your modules, okay? Because we're trying to get you to finish everything up by Thanksgiving, okay? Paper and all that other stuff. Front load this class. Learn to get things done early rather than late. There are certain advantages to that. However, most people don't necessarily believe that. You know, I've always, you can go ahead and start if you want, but I've always gotten in early, and one of my students, graduate students, had a hard time getting in to see me when I was department head. Students have to come see me at 5:30 in the morning, okay? Because I just be, from 9 o'clock on, I just did meetings all day. It's a terrible life. He told me a couple of years ago that the way he solved the problem, he would just stay up all night, come to see me at 5:30, and then he'd go home and go to bed. So, okay, works for him. Okay, we talked about conveying gas and different materials that have been used through the ages, and how we now tend to use a lot of plastic or corrugated stainless steel. And these materials tend to develop different types of problems, okay? Let me go to another one. Another material that has developed problems that were sort of surprising. We used to use carbon steel pipe for sprinkler systems. So this is a fire sprinkler system. And this is one that's actually, you know, spreading a bunch of water. These things actually operate around 200 psi. And so this gets a lot of water. But no one has ever died in a home that's had a sprinkler system in over 100 years, okay? So it works. You might end up with a home that, just like Houston, that's flooded out, but it works. It keeps people from dying in fires. Nonetheless, they decided they wanted to go and save some money. Instead of using copper or steel, they decided to go with plastic, and it turns out it's not the problem with the plastic, but it's the problem that the water comes in on some of the old steel pipes, and the steel pipes, they put a biocide on the inside. They sprayed the inside of the steel pipe with something to keep the bugs and the corrosion down. It turns out that polymer they put on the inside of the steel pipe gets in the water, and it's stagnant water. It's not flowing through in a potable water system. It just sits there, and it cracks the plastic. So there are lots of buildings in this country right now that have sprinkler systems that work all the time, okay? They're leaking. And so there's a lot of secondary effects that you don't always think about, okay, that you run into. I did want to kind of shift gears and take a couple of industries and talk about what's happened in some of these industries. This is the gas turbine industry, so if you're interested in aerospace and engines, it turns out Whittle was the British guy who developed a gas turbine, and there's a nice quote from him, how he invented the gas turbine in like 1936, and then it was during the World War II that it actually kind of came into things, and the Germans actually had V2 rockets and things that had turbines and stuff, some of the first gas turbines. But those original gas turbines, if you go back in time, didn't operate at very high temperatures. In fact, most of them worked at stainless steel temperatures, so you were talking 500 or 700 degrees centigrade, which is not terribly hot. And in any case, people started working on better and better materials, and these were uncooled, solid materials, and they started going to nickel-based superalloys, okay, in the 50s and 60s and 70s. And then they basically came up with as they went to the nickel-based superalloys, they learned you didn't like grain sizes. Finer grain size at high temperature meant creep. The metal would deform. And so they went to directionally solidified turbine blades. They went to single crystal blades by the early 1990s. And in fact, the guy who really led that at Pratt & Whitney was a guy, Bud Shank, who had been a faculty member here at MIT in both mechanical and materials. And he went to Pratt & Whitney and kind of led all that effort in the 60s, okay? But then they went to cooling, and I've sent around again if you want, this thing several times so that you can look at it. I won't pass it around. You probably had a chance to, unless you wanted to see it. But it's got internal cooling passages. And if you take some of the other courses, I'll talk more about how they make that and whatnot. But they went to internal cooling. And the interesting thing here is you see this jump in temperature to about almost 1,300. It eventually got to 1,300 degrees centigrade. That's above the melting point of the material. Okay? If you didn't have that cooling, your engine would melt. Now, the cooling is actually 1,000 degrees Fahrenheit air that comes from the compressor. So as long as the turbine is running, you always have cooling air, okay, unless something gets plugged up. So it's okay. And then they came to thermal barrier coatings. I don't think I passed this one around. This is a stator, but it's got a ceramic coating on the outside. It actually is a lot of technology in these thermal barrier coatings, TBCs, okay? And that allowed them to get to even higher temperatures on a new growth rate curve. You can see when you just had solid metal, there's only so much you can do with the metal when the metal melts at 1250. And these things are getting pretty close to the melting temperature of the metal. And you can't exceed that unless you do some active cooling. And so they have active cooling with thermal barrier coatings, and it turns out all the thermal barrier coatings are zirconium oxide. Anybody know why? Because it's the only ceramic that matches the coefficient of expansion of the nickel. Most ceramics have about 1/5 the coefficient of thermal expansion. You put a ceramic like straight aluminum oxide on a nickel alloy, and it's just going to crack off as things heat up and cool down. Okay? So they actually have to put a fancy metal inner layer, typically intermetallic, nickel aluminum or something that's nice and porous, and then they spray the ceramic on, or actually vaporize it in an electron beam vaporizer, $2 million machine. And each blade may have to be in that machine for an hour as you vapor deposit the zirconium oxide and stuff. That's why these things can cost $5,000 a blade. Okay, they're not cheap. But there's tremendous cost savings as you go to higher temperatures, because this is just what you learn in thermodynamics about heat engines, okay? Delta T over T is the heat efficiency of the engine, right? Theoretical heat efficiency. And now they're predicting here that, we're going to go to other types of silicon-based ceramic matrix composites. These are different materials, and we have different types of coating. And then you have heat pipe cooling in the future, and eutectic oxide ceramic metal composites. Well, don't plan on seeing these things in your lifetime, okay? It's because this is where someone's predicting they're going to have all these fancy things. But why are they doing it? Because every 50 degrees centigrade increase in operating temperature of that engine is worth $2 billion a year to the commercial airlines, okay, in fuel savings. It doesn't take much to end up with a lot of money. So we can talk about the value of a pound saved in a structure, but when you start looking at some engine that's driving it, you can have multiples. And that's why people spend so much money on the engine technology. Yeah.
In that figure, it has silicon-based CMC?
Yeah.
Yeah,
they're not here yet.
Starting back in 2004, is that not something that we've seen yet? Because in 2017, we should be using that for the figure.
This figure was probably developed in 2004 or 5, and people were looking at niobium silicides and things like that because they're actually they're intermetallics, okay? And they have higher melting points. They're not 1250 centigrade as a melting point. They might be 2000 degrees centigrade, but they're brittle as can be, okay? And so no one solved that brittleness problem. And they say, well, we're going to eventually solve the brittleness problem in our ceramics. Well, yeah, good, okay? I'm not invested in that one right now, okay? But people are working on it, okay? And I remember serving on a committee back in about this time frame that was looking at how the Air Force should spend its $300 million a year in research money for engine development, okay? It was a very interesting committee because there were about 40 of us on it. 2 of us were materials people. A number of people were people from General Electric, who was the chief engineer on such and such engine, okay? And one guy sitting next to me one time was the guy who developed the F-100 engine for Pratt & Whitney. I think that was Pratt & Whitney. Anyway, I don't remember which engines were. But there was a problem starting in around in here in the 1990s in that military technology for engines diverged from civilian technology. And the civilians went to high bypass engines. Do you know what high bypass engines are? Getting a lot of nods, okay? So it's just a simple little freshman physics of if you have mass and you have momentum and energy. One's m times v and the other one's 1/2 mv squared, right? I mean, you learned that in freshman physics. And it turns out a high bypass engine, you can blow a lot of air through there so you have a big M, but not as much V, and you get a more efficient engine. But it doesn't have the performance of one of these things that you can just dump fuel in and basically, what do they call them? Well, not a ramjet or a scramjet, but basically, pardon? Well, there's turbojets, but this is basically when you just kind of throw fuel into your afterburner. Pardon me? It's an afterburner, yeah. I guess it's just the afterburner. I remember I grew up in Virginia Beach and we had two naval air stations right there in the Norfolk area. And there was one, I used to pass it every day on the bus going to high school. But one guy was out flying over the Atlantic and he had a flame out and he just turned on his afterburner and he made it back to Oceana Naval Air Station within 100 yards. Kind of crashed within 100 yards but because he just ran out of fuel. I mean, you know, he had probably half a tank of fuel, but to go 10 miles from out in the ocean to Oceana, you burned a whole half a tank of fuel. But you can go really fast, okay? In his case, he didn't have a choice because the main engine had failed. So the military technology was looking for performance and not efficiency. And they started diverging. And that's been a real problem for the whole engine development because the commercial engines before that all built off the military technology. But now they can't because they're heading in different directions in their designs. So anyway, I was sitting next to this guy and they asked us all in the beginning of this committee that lasted for a number of meetings, you know, to go around and what are the key points that we ought to develop? Okay, and these guys from the guys who are the blade designers, okay, that design these cooling passages and things, they would say, well, we need better materials that can go to higher temperatures. And those materials people, we'd say, well, we've kind of gone to the limit of our materials. I mean, I can go back to an Ashby plot here somewhere. I think it's this plot that says maximum service temperature, and there's nothing that goes to 3,000 centigrade, okay? It just doesn't exist, okay? We don't have things that have strong enough bonds. Diamond might do it if it didn't sublime before then or burn in the air. So we would say we needed better designs. Well, this is like a 1975 design, folks. This is our 1980 design. This is not the latest stuff. They're getting these things down less than a millimeter thick, okay? Like a half a millimeter thick, and they have designs of 0.2 of a millimeter thick for the walls. Excuse me? I mean, do you know how hard it is to cast that with any accuracy? They do. The reason we have CAT scanners for metals today, primarily, is because every turbine blade gets a CAT scan, a full CAT scan, to measure the wall thickness. Because you got a core that you cast this thing around and grow a single crystal around this thing, and if that core is off by 2 or 3 thousandths of an inch from its perfect position, and its perfect position is not just a center axis, it's a center axis and a twist, right? you're off by 2 or 3 thousandths over a couple of inches on something that's going to heat up to 1,300 degrees centigrade and melt it and everything else, and it's a piece of junk. Well, all of a sudden you find your manufacturability goes like that, and they continue to make progress because they spend billions of dollars. The problem the Air Force had, am I going in the wrong direction? The problem the Air Force had is they only had $300 million a year, and they wanted to know how to spend it. The other problem that they had, I'm going the wrong way. The other problem they had was that they didn't just want regular old engines. They would be delighted. Well, anyway, I don't really need this one out anymore. They would have been delighted with people developing engines that could go Mach 17 in the air. Mach 17 in the air. I remember going to this meeting and saying, wait a second, who needs Mach 17? Okay, I mean, even the Air Force. I said, why do you need Mach 17 in the air? I said, this is unmanned, isn't it? They said, yes. Okay, so at least I got that right, okay? It wasn't in the air. What happened to my cursor? I gotta, huh? Can anyone see my cursor?
Down at the bottom left.
Oh, there it is. Okay, thanks. So let's cancel that one.
You have to remember that if some is more, or some is good, more is better.
Yeah, well, they gave me an answer which I thought was interesting. Now, you got to remember, this is like 2005. So 9/11 had already occurred, and Osama bin Laden had not yet been captured. But they said that they knew where Osama bin Laden was one time, a year before or 2 years before. This is all classified, and they didn't give us the details. But they knew where Osama bin Laden was. But the closest ordnance that they could get to him, because he was off in some mountain in Pakistan or Afghanistan or somewhere, was on an aircraft carrier about 800 miles away. And they only had 10 or 15 minutes to get the ordnance from 800 miles away to where he was to wipe him out. And they needed Mach 17 to do that. Okay. Well, I guess if you just could shoot a laser anywhere in the world. But Mach 17 is what they go in space with no atmosphere, right? And at Mach 17, your skin temperature is going to be, they had plots for us just from heat flow and friction heating in air, your skin temperature is going to be 10,000 degrees. And I said, there is no material that can do that. They said, oh, well, we'll just use active cooling. And let me tell you what these guys think of for designs. I mean, you're engineers. They were going to do this for the National Air. I'll just tell you about the National Air Space Plane in the 1980s. You know what the National Air Space Plane was? What was it?
Or was that like, I get confused with the X-34, 35, and 43. So
Right. Well, this
like the big transport thing that would come in.
No, this is like Elon Musk. We're going to go from Los Angeles to New Delhi in 2 hours, right? Because you're going to go up into space, and you're going to go Mach 17 up there, and you're going to re-enter the atmosphere, and you're going to do this with all it, for $180 airfare ticket, right? But they were going to have copper as the skin, and they were going to have liquid hydrogen as the fuel, because it's light. Weight is important if you're going fast, right? You've learned that here. And they were going to basically bleed the hydrogen. Oh no, they're going to have the cooling of the hydrogen. And you're going to have on this side of the thing, they would have, back in the National Air Space Plane, it would be 4,000 degrees centigrade would be out here, 4,000 or 5,000 degrees centigrade out here in the air. Okay, that's the frictional heating across the surface, and it would be cooled with liquid hydrogen. This would be a copper alloy. Copper alloys are not exactly known as high temperature alloys, okay? But it's going to be cooled, and this would be, they calculated this should be about no more than 2 millimeters thick, 80 thousandths of an inch. Now, if you ever got a hole, a leak, it's the Space Shuttle Challenger all over again. Kaboom! Because you got hydrogen in air at 4,000 degrees. It burns. Okay? the risk benefit here, okay? Or you know what risk is? Do people know what a risk is defined as? Risk is defined nowadays as the hazard times, now this is done by psychologists, the opportunity, or a consequence, consequence. And so I was actually just talking to somebody yesterday. I used to talk about if I'm manufacturing bricks for a building, I can probably tolerate one bad brick in 1,000 because, you know, if a brick is bad, the guy will probably throw it out, or even if he does mold it into the building's not going to collapse because of one bad brick with a crack in it, right? But if I'm building Hubble telescopes, my quality should be more like 1 in a billion, 1 chance in a billion of failure, because the consequence is you can't fix it, okay, if it's the Hubble telescope. Or actually they did do some fixes, but they're very difficult and very expensive. The hazard here for the National Aerospace Plane was pretty severe. You'll blow up the whole aircraft if you have one small leak across something. And what are the thermal stresses across here? Okay. I mean, there are some thermal stresses, right? 270 minus 270 centigrade and 4,000 centigrade. Okay. And I thought, these are the Air Force's best designers. But they're people designing things to get money, funding from Congress. So it has nothing to do with anything that's practical. You look at these things and you say, is this the best investment of our money? Couldn't we buy potato chips instead? You know, I mean, anyway. Okay, so aside from that, now I gotta find my cursor again or get this thing working. What happened to my cursor again? You can't see my cursor. There's my cursor. Okay, so we did this review yesterday, or a couple of days ago. We did this review, and we did this, and here we had good old Ashby basically pointing out a lot of our traditional metals where development is slow. He said mostly quality control and processing. We've hit the limits on the turbine blades. We've hit the limits on steel. I often point out, since I point out steel is the most important metal in the world, it is the most important metal. It's not the most important material, it's stone. But steel, we spend more money on steel and research on steel than we do on silicon. A lot more. Why? Because the industry is 10 times larger. Even if we only had 20% of the research on steel, it would be twice the research on silicon, even though the percentage research on silicon might be higher. And so I actually wrote an article back in the 90s about the real challenge in materials engineering, and I was saying it was to basically make things less expensive, not to go for tremendous property improvements, because frankly, over the 20th century, we did a lot to improve properties. And we actually are getting to the limits of some of the properties, like the melting temperature, okay? But anyway, so Ashby and other people poo-pooed that. I got the dean of Northwestern University, who's an MIT grad. He's passed away now, but he wrote a vitriolic letter about my having said, you know, that the real challenge was in quality control and processing of materials as these metals. Now, there's all kinds of interesting developments that can go on in polymers and composites and ceramics and glasses, and that's what you read about in the Wall Street Journal and stuff. Okay, let's talk about something that there's Maslow's hierarchy of needs. People, actually, I haven't talked about that in here yet. You know what Maslow's hierarchy of needs are? What are they? It's a little pyramid scheme, right? Not exactly a pyramid scheme, but at the bottom is food, shelter, and clothing. Okay? And then you have other needs, and up here it's self-actualization. Okay? But people first are interested in basic needs of life: food, shelter, clothing, housing. then they can worry about getting an education or other things. And so you can look up Maslow's hierarchy of needs. He came up with this back in the 50s, and now a lot of people criticize it, but nonetheless, it's fairly well known. Actually, I have a good slide. You can find it if you wanted. But there's been some other things added down here to Maslow. There's two other things below this. The first one is Wi-Fi, more important than food and shelter. And the other is battery life, more important than Wi-Fi. Anyway, so we've added to Maslow. In any case, dwellings. I mean, first of all, we made dwellings with the materials we had, which were things like grass, okay? And then people went to stone, and now we do wood and metal and concrete. People thought about concrete homes many years ago. Here's a patent assigned to Thomas Edison, T.A. Edison, for a way to cast a concrete home. Here's your concrete mixer and a little conveyor that dumps the concrete in the top of this mold, and you mold a house. And here's a picture of Edison with his concept, okay? And here's a picture of the house, okay? I think this was in Ohio, but he was going to mass produce these. So talk about a housing development where everyone's home looks the same. I was thinking about this morning, and I was thinking, what are the advantages and disadvantages of a concrete home? Can you think of an advantage or a disadvantage?
You have earthquakes.
You can't have an earthquake? Actually, if it's a small home, you can. I mean, a small block, it's not going to... But you're right, a big building, earthquake, no, you got problems. And part of the problem is I don't think he was doing reinforced steel, reinforced structures and stuff. But yeah, earthquakes could be a problem for big ones. And nowadays, we wouldn't build a structure like this. The codes wouldn't allow it unless we reinforce it with steel, okay? Because of its lousy, or its brittle nature, its lousy tensile properties. Advantages? Fire. Thermal mass could be a very, very good one, although it turns out insulation is better. I mean, stone and concrete actually have low thermal conductivity, much lower than metals, but nowhere near what air gives you when you have fiberglass, insulation. Okay, it just traps a bunch of air. Or polyurethane. Polyurethane is so good that it burns down homes. Because have you ever heard about polyurethane burning down homes? What about polyurethane burning down homes?
They put all the polyurethane foam inside the walls and stuff.
Yep.
And then when it heats up too much, it just combusts.
It's an exothermic reaction for the polymer to polymerize. And it goes up to, well, we got it up to a couple hundred degrees, okay? We just made blocks and cast the polyethylene and just measure, a polyurethane and measure it. But basically, the codes say you're not allowed to put it down in layers more than 2 inches thick at a time. And so if people go in there spraying it in homes, and they would spray it 4 inches, 6 inches thick, and it's such a good insulator that the exothermic nature, it would basically ignite. Okay, and so you burn down your home by putting insulation in. But now they have codes and standards to correct for it. Other thoughts? Fire it's going to be very fire resistant. You can't remodel it. Not only does yours look like everyone else's on the neighborhood, okay, but you can't do much. And can you imagine what people are going to be trying to do? You can't put nails in the wall as easily as wood. No creativity in refurbishing your home. So there's lots of things to start thinking about when you start thinking about these things.
Is that house still around?
I don't know. It was in the 1930s, okay, but they probably didn't cast it until the 1910s or something. But I doubt it's still around because concrete actually, the Roman concrete lasts for thousands of years, and that's an interesting study, and I've had students do papers on that. There's a lot of science behind Roman concrete and why it lasts for 2,000 years, and modern concrete typically doesn't last for more than 100 or 200 years. And it has to do with the volcanic ash that they used to make the concrete, and you get a certain chemistry. I don't know that much about it, but So concrete
There's a
will
couple
last.
houses that still exist.
Are there? Yeah, okay. Where are they, do they say?
303 North Mountain. Um,
North Mountain what? Lots of
Avenue.
North Mountain. Oh, okay, well, in some state. Okay. So you could go ask the neighbors what it's like to live in a concrete house. Actually, people have been living in concrete block houses. Actually, that was a project that a student did once. She was from Mexico and she did adobe. Okay. And adobe, I didn't know, but they tend to use manure for the adobe in many cases because it keeps the flies away. So it's just straw and manure. Okay, and you build your house out of that. One of the problems is it does smell for a few years. Anyway, melting of metals. Okay, I want to talk about metals now rather than concrete. But people will look. I guess I just brought up the Edison and his concrete home as an example of people looking for different things to use things. In concrete, they look at because it's cheap. Okay. You can't exactly move that home. You'd be cheaper to blow it up than to move it. It's kind of heavy. But metals, on the other hand, were not used in earlier times. In fact, it's very much because they were very expensive. And it turns out they used to burn down old wooden buildings that had nails in them to recover the nails from the ashes. Okay? That's how valuable the nails are. And that's because it took about a person years of effort to make a ton of cast iron or steel 400 years ago, and now it takes 20 minutes or less, okay, of labor content. And I talked about that. But some of the problems were the first metals were not steel and cast iron. The adiabatic flame temperature in air of burning carbon or hydrogen in oxygen in the air is about 1,000 degrees centigrade. Copper melts right near here, so you can build a kind of little furnace that will hold the heat or preheat the air coming in, and you can melt copper, or you certainly can make bronze with some tin that lowers the melting point of the copper. For years, we could not melt steel, and I'll talk about that. Cast iron melts at 1150, so you can actually build a blast furnace. And this is a picture of an old blast furnace. You have some guy at the top precariously here. He's dumping coal and limestone and iron ore into this blast furnace. There's bellows here. If you go to Saugus Iron Works, this is the Saugus National Historical Site, the first cast iron foundry in the United States. There's actually a water wheel. That's the sluice for the water wheel. And this is the platform. They drop the stuff in the top. This is actually the chamber, the stone blast chamber. And the sluice would run a bellows that blows the blast of air in here to get up to the 1150 degrees that you need to melt cast iron. And cast iron was a strategic material militarily because that's what your cannonballs and your cannons were made out of. The first cannons were made out of brass, but they weren't as strong and they were expensive, and eventually people developed cast iron. So if we go to steel, you've already heard about it's got unique things, and then you can form it in soft condition and then harden it. I did a paper in my junior humanities class on the hardenability of steel, learning how to harden steel. And it goes back thousands of years. People made swords in quenched and tempered steels, okay? And the Achilles heels of steel are corrosion, hydrogen, cracking, and low temperature toughness, which we've talked a little bit about. And that was part of the Liberty ships, and that's why you need fracture energy. Now, if you go to the history of steel making, we had two types of steel. We had cast iron, wrought iron. Anybody know the difference between the two of them? Pardon?
One's forged, one's cast.
Yep, but why? What's the difference in the composition? Cast iron is like 3 or 4% carbon and is very brittle, unless we now learned after World War II how to make it ductile. We call it ductile iron. But the traditional cast iron for thousands of years is very brittle. The wrought iron, you basically take cast iron and you blow air through it. And they called it puddling of iron. And people would just blow, have bellows and blow, and they burn the carbon off. And then they would end up with something that's mostly iron with very low carbon, and now it can be forged and beat into, by blacksmiths into useful things. Yes?
So if it's only at 700C, is it just diffusion?
Oh, I'm going to talk about that. Okay. Well, it is a diffusion process to smelt it. Okay. You don't melt it. You actually take the iron ore, put it in with a bunch of charcoal, put it in an oxygen depleted environment, and you get a reducing carbon monoxide atmosphere, which reduces, and you get sponge iron. You basically get something that looks like a sponge. It's all porous, and you have to forge that back into a solid chunk. And you lose 50% of it by oxidation in the forge, okay, as you're pounding it to get all the pores out of it. But it is a solid state process at 700C. They later learned to basically not do this at 700C, but to take the cast iron and blow oxygen through it and make puddled iron, okay? That's at higher temperatures. And that's what they were doing in the 1850s when Bessemer came along. He was trying to improve puddling of iron, and he learned a way to make steel without puddling it, okay? But this is low carbon. It would be forged, and high carbon has to be cast and is brittle and cannot be forged. It will break when you hit it. If you look at the iron carbon phase diagram, which we won't go through, but here's pure iron at 1500 something centigrade melting temperature. If you add 3 or 4% cast iron, you get a eutectic that's just under 1200, 1148 C. You have different phases in here that we don't have to go through, but they didn't really know, well, they didn't even know what a phase diagram was until J. Willard Gibbs came along in the 1870s and told them what a phase was. And then in the 1880s, they developed metallography, and that was the beginning of metallurgy. MIT didn't start out with the Department of Metallurgy, it started out at the Department of Geology, okay? And it became the Department of Metallurgy in 1888 because this guy in England learned how to polish things and look at them in a microscope and see the structure of the material. And so this guy, Robert Austin and Adolphe Martins in France, Martensite and Austinite, and they all have geological names like ite on the end. Ferrite just means iron mineral, right? But that's because it came out of geology, so far as that goes. You had this guy who was one of the greatest British scientists of all time, people say, because in 1856 he developed, this is his original Bessemer converter. He would take the cast iron and he would blow oxygen in here, and he essentially came up with a way to make puddled iron where you blow air into cast iron and turn it into steel. And that's the beginning, the Bessemer age, of Andrew Carnegie becoming the richest man in the world, when he basically, it's an interesting story. That could be a good paper, is the paper of how Andrew Carnegie did some sort of shady things in Pennsylvania and ended up with part of a steel company. But he became the richest man in the world, so far as anyone we know in modern times, in constant dollars. And there, you can see the environment he produced for everything. But he actually was a very kind Scotsman in many ways. When you're that rich, you can be kind. Take away my people, leave my factories, and soon grass will grow on our factory floors. Take away my factories and leave my people, and soon we will have new and better factory. That's not the philosophy of most businessmen today, but Andrew Carnegie was, they sort of were competing to be well thought of after they raped and pillaged the economy. Roosevelt, who started Standard Oil, used to go around giving away dimes. But a dime was sort of like a $10 bill nowadays, okay? He'd just go down the street and hand out dimes to people. That was Rockefeller, sorry. I actually have a good story on Andrew Carnegie and my grandfather, but we'll do that some other time. My grandfather helped start the University of Chattanooga, and he got the last money from Andrew Carnegie. But anyway, Andrew Carnegie's real thing, just like Bill Gates wants to improve health in the third world, Andrew Carnegie's thing was education. So there's Carnegie Libraries, Carnegie Mellon University. He gave a tremendous amount of his fortune away to universities. Integrated steel mills, okay? It turns out most of the world's steel is still made in integrated steel mills. The last commercially built steel mill, integrated steel mill in the world, was Burns Harbor, Indiana, built by Bethlehem Steel, started in 1964, finished about 10 years later, and right here on Lake Michigan in Indiana, and this is only part of it, okay? It stretches for miles. It's as big as the MIT campus and a lot more industrial. I've estimated in the past that it would cost $20 billion today to build an integrated steel mill. It turns out it is the most productive steel mill in the United States by far because it's the only modern one. When I worked for Bethlehem Steel, they were very proud of the fact their blast furnaces were built in 1912 and their coke ovens were built in 1911. And the guy said, and it doesn't cost us anything to make steel because all our equipment's fully depreciated. And I asked him, well, why is that? And he said, oh, that's because you don't understand finance. Well, I later learned that this vice president of finance didn't understand finance, and that's why Bethlehem Steel is bankrupt now. But nonetheless, the Japanese had to build new steel mills after World War II, and they built them. And they were beating their pants off in the 1970s with better quality steel at lower cost. Typically, these will be 5 million tons per year, several blast furnaces, and these blast furnaces can run for 2 or 3 years before they shut them down now, okay, to reline the ceramics and stuff. And that's based on $180 a ton hot metal, which was the price in the 1970s, and it's still the price today, okay, not constant dollars. Actually, the price has gone down by about a factor of 3 because inflation has been about a factor of 3 since then. But the blast furnace takes all these things and it basically has stoves. And there was just something on the MIT website about someone had this new idea to use an old technology to worry about solar energy and things like that. They're going to have hot bricks. Well, people have been using hot bricks to hold the heat as just a massive bunch of bricks. Every blast furnace had 2 sets of brick stoves, and you would have your exhaust gases go through one, heating up the bricks, and your incoming air going through the other, which had hot bricks. And every 12 hours, you would shift the flow to reheat the cold bricks and use the heat from. So it's a heat recovery, okay? They do the exact same thing in glass furnaces, okay? Because the energy cost is such a big fraction, you have to do something to conserve your energy. So if you look at this is an open hearth process. This is what Andrew Carnegie had, and you have these huge, they don't show them as big as they really are. They're about the size of a football field and about 2 stories tall. Just brickwork, lattice work of bricks, okay? The actual furnace is not much bigger, well, it's a little bigger than this room, maybe twice the size of this room, but it's not the size of these 2 things. The brickwork is a couple of football fields. But then in the 1950s, and I'll finish with this, there was a guy in Austria who decided all you're doing in the other furnace is basically the Bessemer process of passing hot air over cast iron to burn the carbon off, to turn it into a lower carbon version, which is basically steel. He decided, well, why don't we just use pure oxygen? Because the Germans had developed the Lindy process for liquefying air, and you could get pure oxygen. So they built a Bessemer not a Bessemer, but a basic oxygen furnace. And it used to take, in the old open hearth process, which would be 400 tons of steel in here, it used to take anywhere from 24 to 48 hours to process that 400 tons of steel. In a BOF furnace, which they started building in the about 1960s or so, by the 1970s it had taken over the entire industry. Last basic open hearths, the last one was built by U.S. Steel in early 70s, and they were stupid to build that one, okay? This processes 300 tons of steel in 20 minutes. Yeah.
So I've been to a forge and they were like making parts and just kind of like putting them outside to cool down. Do you end up with differences in your material properties because you're uncontrolled cooling atmosphere and I assume the cost isn't worth it to build like a controlled cooling room?
If you have low carbon forged steel, you can do that. You have higher carbon stuff and it cools down too fast, you'll get martensite and it might crack, okay? So in a very high quality forge shop, okay, you would have furnaces and you do controlled cooling, okay, on big parts. But small parts, I mean, if you're talking parts this size, a lot of times you actually, if it's the right size part, air cooling is great. It's called normalization, okay? It's actually a heat treatment step. But for the majority of forged parts, they do something to control it. But if you're low carbon steel, if it's just you're forging some hinge or something and it's not critical, it's not a big deal. But most of your forgings are medium carbon and high carbon going into turbines and things, and you did that, General Electric would fire you right away. Yes?
What's the fuel for these furnaces? Is it coke?
The fuel in this one is oxygen. Oxygen burning the coal, the carbon out of the cast iron. I got 4% cast iron carbon in that cast iron, so I got 12 tons, 4% times 300 tons of cast iron, and I blow through pure oxygen in there. There's plenty of heat. I burn up 12 tons of coal. Right. Just and that 300 tons, this whole thing stands about 4 or 5 stories tall, okay? And this is maybe only 4 or 5 feet tall in the bottom. And when they blow the oxygen in there at supersonic, pure oxygen, supersonic velocities, this becomes a froth and fills up this whole 3 or 4 story tall container, okay? And it's just a foam. It is fireworks galore, okay? It's real exciting. You're not allowed to stand anywhere, well, you got to be in the doghouse, which is where the control room, which is, you know, insulated and everything, or you got to be outside the building. I mean, there's literally sparks just flying. It's very, very violent reaction, but it's very efficient. Like I said, it takes a 20-minute blow to get all the carbon out. Whereas the old days, when you just had a boundary layer and you just blowing air across the top and you didn't get a froth, okay, it could take, you know, a day or two. And that's one of the reasons we'll go through the productivity next time. But the productivity has gone from about 3,000 hours per ton of cast iron back in the days of Saugus Iron Works 400 years ago to about 20 minutes today per person hour to produce it. And that has made a world of difference. And that's one of the reasons why steel is so widely used. It's cheap because they have spent so much money. And I'll show you the curve that I came up with. And it's really dramatic. It's a log plot of cost going down, okay? And it's getting steeper, okay, in recent years. Okay, we ran over, sorry.